So we are going to start the new point of our syllabus is conformations and configurations. So first point, difference between the conformations and configurations. So the first difference between these conformations and configurations. So definitions of conformations is conformations refers to different arrangements of atom in molecules. They can readily interconvert. So definitions of configurations is configuration refers to different arrangements of atom in molecules. They cannot readily interconvert. So this is first difference between the conformations and configurations. So second difference is related with the convergence. So the convergence of one conformation into another conformation is possible in conformations, but in configurations there is convergence of one configuration into another configurations. It is difficult. So this is the second difference related to the convergence. So the next, that is a third difference related to the flexibility. So conformations are flexible, but configurations are less flexible. So the fourth difference is related to the separations. So conformations are less separables, but configurations are separables. And so their fifth difference is related to the rotations. In conformations, rotations of carbon-carbon single bond is take place, but in configurations, so there is a rotations of carbon-carbon single bond do not take place because of there is a breaking and making of new chemical bonds is take place. So this is the first point of our syllabus, that is the difference between conformations and configurations. So next point, hydrogen bondings. So in which molecule there is hydrogen bonding is take place. So if we consider the simple example, A is it is a proton donor group. B is nothing but the electron donor group. So A is nothing but the electronegative element, H is nothing but the electropositive elements. And so this H molecule, it donates the protons, so it is nothing but the proton donor group. B is nothing but the electron donor group, it having the lone pair of electrons or pi bondings, and so therefore there is a bond between B and H. There is a weak bond between A and B is formed, and so this bonding is nothing but the hydrogen bondings. So next there are two types of hydrogen bonding. One is intermolecular hydrogen bonding, and other that is intramolecular hydrogen bondings. So intermolecular hydrogen bondings, there is this hydrogen bonding is formed between the two molecules. Two different groups have two different molecules, and so in that between these two molecules there is formations of hydrogen bonding. This is nothing but the intermolecular hydrogen bonding. Example, that is water and ethanol, that is alcohols, any alcohols, and so therefore there is a weak bond is formed between this water and alcohols. So this is nothing but the intermolecular hydrogen bondings. So another type, that is intramolecular hydrogen bondings. This hydrogen bonding is formed between the two groups of same molecules or two same molecules. This is nothing but the intramolecular hydrogen bonding. Their example is acetic acids. In acetic acid, there is formations of intramolecular hydrogen bonding is take place. So in this way, there is a weak bond is formed between these two groups of two same molecules. So this is nothing but the intramolecular hydrogen bonding. So another example, that is salicylaldehydes. So in the salicylaldehydes, there is also formations of hydrogen bonding is take place. So in that case, there is this type of weak hydrogen bonding is formation take place. This is the example of intramolecular hydrogen bonding. So this intramolecular hydrogen bonding is take place in the acetic acids and salicylaldehydes, and intermolecular hydrogen bonding is take place in the alcohol and waters. So next point, that is conformations and intramolecular hydrogen bondings. So if we take the example, that is ethylene glycols, and another example, that is 2-chloroethanols. So in that molecule there is a intermolecular hydrogen bonding formations is take place. So what is the conformations? There are different type of conformations: eclipse conformations, Q conformation, Gauch conformations, staggered conformation. These are the different type of conformations. So these conformations also observed in this here in the intermolecular hydrogen bondings. Another, that is type of, there is a number of examples. There is the formations of intermolecular hydrogen bonding is take place. So first we have to consider example that is ethylene glycol, CH2 CH2, CH2OH, CH2OH. Another example, that is 2-chloroethanol. So in that, these two example, in that compound there is a formation of intermolecular hydrogen bonding is take place, but this is studied by using the conformations, that is eclipse conformation, Gauge conformations, anti-conformation. These are the different type of conformations used and to study the intermolecular hydrogen bondings. So firstly, you have to consider example, that is ethylene glycols. So in the Gauge conformations, firstly it is in the antiform. This structure is present in the antiform. Next, that is Gauge conformations. OH is present in this here. This OH group is present in this here. So there is hydrogen bonding is formations take place between these two. Firstly, structure is present in the eclipse form, so at that time this bond angle is 0 degree. So at that time this OH group comes too close to each other, so at that time it undergoes reflections, and so there is to disturb their stability, and so to maintain their stability it requires the very high energy. So at that time eclipse conformation at 0 bond angle, at that time there is no formations of hydrogen bonding is take place. But this structure is rotated into the 180 degrees, so at that time this OH group goes far away from each other, and so in this way there is in antiform there is no formations of hydrogen bonding is take place. And there are two gauge form. This is one gauge form, this is another gauge form. So in this here this structure is rotated into the 60 degree, so at that time there is hydrogen bonding is formed is take place in between these two groups. So another, that is this structure is rotated in the 300 degree. So at that time in that compound also there is formations of hydrogen bonding is take place. So this is for this is nothing but the intermolecular hydrogen bonding in ethylene glycol. Next, another example, there is 2-chloroethanols. Same in antiform, these two bulky group, that is OH and Cl. This group goes far away from each other, and so there is no formations of hydrogen bonding is take place. But in Gauge conformations, here is Cl, here is OH. In this here there is a intermolecular hydrogen bonding formation is take place. So here is OH, here is Cl, and so this H is here. So in this here also there is formations of intermolecular hydrogen bonding is take place. So in the 2-chloroethanol, in a solid, gaseous or liquid state, in 3 different states, in a 2-chloroethanol there is a formations of intermolecular hydrogen bonding is take place. So this is nothing but the intermolecular hydrogen bondings, their definitions, and there are two types of hydrogen bonding, that is one is intermolecular, another that is intermolecular. So there are examples, and there are conformations and intermolecular hydrogen bondings. So next point, 1,2-dihaloethanes, conformations of 1,2-dihaloethanes. So in this here, if you consider 1,2-dichloroethanes or 1,2-dibromoethanes, so in that compounds, in a solid state or in a gaseous state or in a liquid state, what will happening? We are going to study in this here. So if you consider the 1,2-dichloroethanes or 1,2-dibromoethanes in gaseous state at 22 ounces Celsius temperature, so at that time what will happen? So this compound, there is 3 forms are equal. There is antiform is more populated in the gaseous states at 22 ounces Celsius temperatures. If you consider 1,2-dichloro or 1,2-dibromoethanes, in a gaseous states there is a antiform is more populated. That is nothing but the 73% and 85%. Compared with the n-butenes, there are antiform is 67%. So if you consider in the liquid state, if you consider the example that is 1,2-dichloroethanes or 1,2-dibromethanes, in a liquid state there is Gauge conformations are more populated than antiforms. So we are taking the example that is 1,2-dichloroethanes or 1,2-dibromethanes. So if you consider that 1,2-dibromethanes in a liquid state, their Gauge conformation is more populated, that is 35%, and their conformational free energy is 3.5 kilojoules per moles. So if we consider another example that is 1,2-fluorobromose or 1,2-chlorofluoro or 1,2-fluoroiodoethanes. So all those compounds, if we consider in the gaseous states, their antiform is more populated. And in liquid state, their Gauge conformations are more populated compared with the N hexanes or N butanes. So if you consider the 1,2-dichloroethanes in gaseous states, their Gauge anti-conformations are more populated than Gauge conformations, and in liquid state, their Gauge conformations are more populated than anti-conformations. So their conformation energy of 1,2-dichloroethanes is 12.1 kilojoule per moles. It is same to compare with the ethanes, their conformations and free energy. So this is the conformations of 1,2-dihaloethanes. In this here, you have to consider in a gaseous state and in a liquid states. So what will happening? And you have to consider the example that is 1,2-dihalo, 1,2-dichloro or 1,2-diabromoethanes. You have to consider another example that is 1,2-fluorobromo, 1,2-chlorofluoro or 1,2-fluoroiodo. All those compounds in the gaseous states, their antiforms are more populated. And in the liquid states, their Gauge conformations are more populated. And so their 1,2-dibromoethanes, their conformation free energy is 3.5 and their Gauge conformation is 35%. And so if you consider example that is ethanes, so their conformation free energy is 12.1 kilojoule per moles, and so this energy is same to the ethane. Next point, conformations of 2,3-dimethylbutenes. So in all temperatures, if you consider, we have already studied the conformations of 1,2-dihaloethanes, so it is considered in the gaseous and liquid state. But in if you consider these two examples, that is 2,3-dimethylbutenes, in all temperatures, there one Gauge conformation, two Gauge conformations and one anti-conformations, all those are equally populated in all temperatures. If you consider another example, that is 1,1,2,2 tetrachloroethanes or 1,1,2,2 tetrabromoethanes, you have to consider this example. In that example, also same observed. In that compounds also, there is all temperature, they show the three forms, and all those three forms, they are equally populated. One is antiforms, another two is Gauge form, antiform is a chiral form, another two form, that is they show the diastereoic form. So in this way, it is also observed in some other examples. If you consider in all temperatures, if you consider 2,3-dimethylbutenes, so in the 2,3-dimethylbutenes in eclipse conformations, at that time this bond angle is 0, and so at that time there is a rear and front methyl groups come too close to each other, and so there is a repulsion is take place in this years, and so the stability of the structure is disturbed, and so to maintain the stability it requires very high energy, that is 18 kilojoule per moles and 33 kilojoule moles at the bond angle 0 in eclipse conformations. So at that time, it is not convergence take place from Gauge to Gauge conversion cannot take place in this year in 2,3-dimethylbutenes. In this year, there is intermediate anti-convergence is take place. So this is nothing but the, if you consider this example, so first that is CS3. This is the Gauge conformations. In the middle, there is a antiforms, and finally last that is it is converted to the Gauge conformation. So intermediate, that is anti-conversion is take place directly, cannot it convert into the Gauge to Gauge conversions cannot take place in this year. Okay, thank you.